Okay, please don't get too downhearted when you see the length of this PowerPoint. There are just a lot of visual things that we're going to be doing as we work through this material. So just relax and you'll all survive. But what we're doing is uh, breaking this up a little bit different than I have in the past, and I hope it makes understanding better. But what happens here is 7.1, we're going to talk about estimating the population proportion. We're going to talk about confidence intervals. 8.1 is a general introduction to significance testing. 8.2 is specific significance testing to proportions, and 9.1 has to do when we're looking at the difference between two population proportions. So that's where we're going to go in this section of Unit 4. I'm going to break this down into smaller lectures, but the PowerPoint goes for all four of these sections. So let's start with 7.1. Okay, now in chapters 2 and 3 we looked at descriptive statistics, and we specifically looked at the mean and standard deviation. And then in chapter 6 we talked about z-scores and the area to its right using that subscript notation, that subscript notation. So we're going to talk about that. And remember, in chapters 4 and 5, what we did was we talked about probability. And that's what statistics is how do we deal with probability. So we're going to be using sample data to estimate population parameters. We're going to be dealing with proportions, means, and we will be doing standard deviations. So we'll be doing proportions, mean, and standard deviation. Why won't this write? We'll be doing proportions, means, and standard deviations. This isn't working. Why isn't it working? So we'll be doing proportions oh man, that's why I'm using this crazy thing and I'm not being able to use it. So in this section we'll be doing mean, standard deviation, and oh, never mind, this isn't right. So we'll be looking at how we're going to estimate parameters, proportions, means, and then we're also going to be doing standard deviations. And then what we're going to do in the Chapter 8 sections is we're going to be testing hypotheses. And another word you can think about that is claims. So we're going to start with estimating a population proportion. So that's what statistics does for us. It allows us to gather sample data and use that to make inferences about a population data. And so remember, a sample proportion would be a statistic, and a population proportion would be a parameter. And what we're going to do is we're going to construct a confidence interval, and then at the end of this section we're also going to estimate the sample size needed to get a good estimate. So we've got a couple different kinds of estimates, and the first one is a point estimate, and that is just a single value. And so we're going to use our sample proportion to estimate our population proportion. And you know, and I know, when you're making a good guess, when we do a single point, we can be off a little bit more. But the good thing about this is this is an unbiased estimator, so it's a good estimator with no built-in error. So let's look at this situation, and this is one of the reasons why the number of slides is so many, is because we have a lot of multi-slide examples. So we have took a survey of 1,487 adults, and 43% of them have a Facebook page. So p hat, which is the sample proportion, is p hat is the sample proportion. It's the best estimate of the population proportion. So this single point estimate, we would estimate that 43% or 0.43 of the population of all adults have a Facebook page. But when we are estimating, if we estimate a range, we're more often to be right. So let's back up just a little bit. And an example of a single point estimate would be trying to hit a target with a rifle. Okay, you've got to be pretty good to get the bullseye. When we do a confidence interval, it's more like hitting the target with a shotgun. So when we hit that target with a shotgun, what's going to happen is we're going to get around that bullseye, and the area covered by the shotgun blast is probably going to include the bullseye some way. So that's what we're talking about when we do this. So this is called an interval estimate, and we always have an estimate plus or minus our margin of error. And what's going to happen as we do this, our estimate is going to be our statistic. And what's going to happen is, in this case, our estimate's going to be a p hat, and then we have a formula for our margin of error. We're going to look at means, and our estimate is going to be the sample mean plus or minus a margin of error. And then we're going to look at standard deviations plus or minus our margin of error, and we'll go through and we'll look at that. But right now in this section we are concentrating on proportions. So we set up our confidence interval, and our confidence interval is 1 minus alpha. So remember, if we were going to look at a distribution, our alpha would be out in the tail. Well, our confidence interval is in the middle. So we have standard confidence levels of 90%, 95%, 99%, and they correspond with alpha of 10%, alpha of 5%, alpha of 1%. Now here's a picture of what's happening. So here is what we're talking about when we talk about a confidence level or confidence interval. We are confident in the process, and in the long run the results of that process should give us an interval that does contain the true value. So you can see we have a whole bunch of samples of the same size from the same data, and if we look at them, the true mean is captured in this case 19 out of 20 times if the true value was 0.5. But remember, when we set an alpha of 0.05, we're willing to be wrong 5 times out of 100 or 1 time out of 20. So when we look at our confidence interval, we're 95% confident that our interval actually does contain the true value of the population proportion P. So this is back to the Facebook example. So let's look at how we do that. So we're going to sample 1,487 adults, and we're going to construct a 95% confidence interval. And remember, that refers to the success rate of the process. Now, in your book they give you great examples of incorrect interpretation of confidence intervals. Read them, but I did not want to put them in your mind, so I'm not going to talk about them. And then remember, if we have overlapping confidence intervals, they shouldn't be used to make conclusions that two groups are equal. Okay, so again, what we have is we have a critical value, and your book talks about the critical value as z sub alpha divided by 2, meaning that alpha is the area in both tails. We're just going to look up the area in one tail. Now, in other textbooks, they call this critical value z star, and I may do that, and you may see slides with that in that. So the critical value can be noted either way. So again, if we want alpha as 0.05, then we know our confidence level is 95%. If alpha is 0.5, then we know there's 2.5% area in the upper tail and 2.5% area in the lower tail, and we're going to look for those critical values. Now, here's the deal. This is a pretty standard confidence interval, so I have some pretty standard critical z-scores, and for 95% the critical z is plus or minus 1.96. And so again, we know that the other 95% is in between our critical values, and this will add up to 95%. I think I said that. And so we can find table A2 to find that critical value. Now, here is a table of the critical values, but on the bottom of A2 from your barrel fold tables in the eText, there in the bottom right hand corner there's a little table that gives us that same information. So let's look at page 311, number 5, 6, and 7. Okay, so number 5 says let's find the 90%, the critical value for the 90% confidence interval. So that means there's 10% outside. So let's think about that. There's 10% in both tails. So that means there's going to be 5% up here in the upper tail. So we want to find the area to the left that corresponds as closely as possible to 0.95. So let's look in the table, and what you can see right here is 0.9495 and 0.9505. Well, here's the deal. They're both the same distance, so we're going to go right in between. So our critical Z is going to be a positive and negative 1.645. Does that make sense? Now, if we go to the bottom of this page, and I've got to get rid of my writing ability here, but if we go to the bottom of this page, this is where those common critical values are, and then right there is my right there is my critical value. So I found it by the table, and I found it using that little table there. Now let's do StatCrunch and show how we would do that. And I'm going to do Stat Calculators Normal, and we can do in the bottom we don't know this, so get rid of it, and we want this to be 0.05, the area in the lower table, the lower tail, and we do compute, and there we get 1.6448, which rounds to 1.645. Remember, with a confidence interval, we always have are thinking both tails. So when we find our critical Z here, it will always be both positive and negative. Okay, so let's go back and let's do number 6, and it's a 99%, and let's just use our same screen here, and we'll do that. And if it's 99%, it's 1% outside, which is 0.01, and half of that is 0.005. And then I'm going to compute. And there is my critical value. And again, because we're doing so there I have my critical value, and because we're doing a confidence interval, remember we're also considering that very top tail. So our our critical z, and remember we do it like this, alpha divided by 2, is going to be plus or minus 2.58. Okay, let's go back to the table and let's do the same thing. And again, they do this one, they take it out to 3 places, and the reason is here we are, we wanted 0.001, sorry, which we'd subtract that, and that 0.000, anyway, this one is 1 too low and this one is 1 too high, so we're going to go halfway in between, and that's how we get that critical value for so where this one is a little too low and this one's a little too high, so we're going to go halfway in between, and that's how we get the critical value for a 99% confidence interval. Let's jump up and let's do number 8, because that's not on our table, and that is a 98% confidence. So let's look at that. And so let's think about it. So let's draw our picture. So we want 98% in the middle. That means there's 2% on either end, so we know there's 0.01 here and there's 0.01 here. So I want to look up a number that has 0.9900. So let's find a number that's as close to that as we can, and you can see here we go, 0.9901, 0.9908. This is 2 below, this is, sorry, 0.9898, this is 1 above, so this is a smite closer. So there's our critical value, so we know it's going to be 0.23. So it's going to be 1.2 and then 3, I believe, is what we want there. Sorry, it was, oh man, it was 2.3 was what we found on the lower table, and then our last digit is 3. So our critical value is going to be a plus or minus 2.33. Now let's do that on StatCrunch. And if you find it easier to use StatCrunch than to use the table, you go for it. But here's what I want, and let's just do the upper tail for a change. And I want to get rid of this. And remember, I wanted 1% above. And so I'm going to compute, and there I get that same answer, 2.33. And then remember, because we're doing a confidence interval, that will be plus or minus. So let's talk about the margin of error. So any confidence interval is our estimate plus or minus our margin of error. And the estimate is the statistic that we can easily calculate. But the margin of error is our maximum likely difference, and so it's actually the maximum error of estimate. So here's the deal. When we're doing a proportion, this is our formula. So this number is simply our critical value. The stuff under the radical sign is our estimated standard deviation of the sample proportions. And P is our sample proportion, Q is its complement, and N is the number in the sample. It's going to be important to remember to round our error to 3 significant digits, and we do that in the very last step. So what has to happen so we can do this? Well, first thing, it needs to be a simple random sample. And the second thing, we need to satisfy the conditions for binomial distribution, which means we have a fixed number of independent trials. We have two options, success or failure, and that the probabilities remain constant for each trial. And here's the kicker. There needs to be at least 5 successes and 5 failures. So you can have a relatively small sample size if requirement number 3 is met. And here's how we write them. We can write them with less than signs between. We can write it as a statement of plus or minus, and we can write it using interval notation. And remember, this is our low, this is our high, and then we use parentheses, meaning that the ends are included in our interval. So let's do a problem. Okay, so let's go back to that sample, and remember we talked to 1,487 and we found that 43% had a Facebook page. So we are going to look at this, and so here's what we want to do, and let's think about this while we are looking at this. So we want a 95% confidence interval. So we know our critical Z for a 95% confidence interval is going to be 1.96. And now when we're calculating our error, we only use the positive end. So we're going to find the margin of error first, then we're going to do our confidence interval, and then we're going to write a summary statement. So that's our plan of attack. So we do the requirement. We have a simple random sample. The binomial conditions are satisfied. We have a fixed number of trials. They either have a Facebook page or do not. And then we know that there are 639 successes, and that means we have 848 failures. So we're good with the requirements. So let's look at this. So I did this on StatCrunch, and you can see my breadcrumb trail. And so one sample proportion summary, I'm going to put in my number of successes, my number of observations, and the standard walled comes up. If you've read in your textbook, there's a way that is a little bit more precise, but we're going to deal with the standard wall because we're just learning how to do this. And so what we have, I did this, I hit compute, and here is my output. So it tells me my sample proportion, it tells me my standard error, here is my lower limit, here is my upper limit. So let's write this. So we could say our proportion is less than 0.45, and we want to go 3 significant digits, 5 on the upper end, and it's greater than 0.405. So I could write it like that. I could write it as my p-hat 0.43 plus or minus 0.0128, or I could write it as interval notation 0.405 on the low end and 0.455 on the high end. Now let's do it, look at the formula to do it by hand. So we're going to do the math, and this is what we got, and guess what? They get the same thing we got. Now here is C, and here's the deal. It does appear that fewer than 50% of adults have a Facebook page because the interval values from 0.405 to 0.455 does not include 0.5. And you can read through that. So let's look at page 312. So let's look at page 312 and look at number 14. So it talks about the drug Eliquis. And it says it's used to prevent blood clots in clinical trials among 5,924 patients. Okay, so N equals 5,924, and this is number 14. And the number of successes is 153, and it says they developed an adverse reaction of nausea. Now, even though nausea doesn't seem to be very successful, that's what we're looking for, so that's what we count as successes. So we want to construct a confidence interval of 95%. So first, let's do a little homework here. And let's think about this. And so my critical Z for 95% confidence interval is going to be 1.96. And I need to come up with my p hat, which is my number of successes over my total number of trials. And I get 0.0258. Okay, so remember we want to do our estimate plus or minus our error. Now, while we're here, let's just go ahead and calculate our Q hat, which will be 1 minus our P hat. And that will come out to be 0.9742. Okay, so we know our estimate is our P hat, and we know our error is our critical Z times the square root of P hat Q hat all over N. And remember, this is our estimate of our standard deviation. So let's go ahead and let's plug these numbers in. And the number in our sample is 5,924. When I do the stuff under the radical, I get 0.002058. Now I took it out a lot more digits than I needed to, and I will round it at the end. Since I have it on my calculator, that's not a big deal. And so 0.0258 plus or minus 0.004. Now this is where I'm going to round it to 3 significant digits. It's 40372204. I'm going to round it to 4004. 004. Three significant digits. 1, 2, 3. Okay, so there's my answer. They get a different answer. Oh, because I didn't follow directions. Okay, let's start over. We wanted a 99% confidence interval. So I want a 99% confidence interval. And so my critical Z is going to be 2.575. So we're going to put that in here, 2.575. So let's do that. 0.00200598 times 2.575. There we go. There's two significant digits, and that makes it 3. Except they rounded it up. Okay, and so then my answer is going to be, let's add that. So on my high end, it's going to be hello. What do you need? Oh, okay, and you want that? Okay, I'll be over in just a bit. Bye. So on the high end, we have 0.0311, and our population proportion will be less than that, and it will be more than 0.0205. All right, so we can write it like this, we can write it like this, we can write it like this. Now, what does that mean? That means that the true population proportion of the people who take Eliquis who develop an adverse reaction is somewhere between about 2 and 3%. And we're sure of our procedure. We're 95% sure of our procedure on this. Here's what it says in the book. We have 99% confidence that the interval from 0.0205 to 0.0311 actually does contain the true value of the population proportion of all Eliquis users who experience nausea. So that's how we would do this one by hand. Okay, now let's do that same problem with Eliquis on StatCrunch. What we're going to do is we're going to go to Stat, Proportion Statistics, One Sample with Summary. Now we would use with data if we had the data in a spreadsheet, but we've got the summary. So what were the number of successes? The number of successes there was 153. Our number of observations is 5,924. And here is the trick. We're going to do the confidence interval. Now, don't misread it and make sure you follow the directions. We don't want 95% or 95% confidence level. We want a 99% confidence interval. And we want to use the standard walled, and we want to compute. And here we have it. So there's our lower limit, which is exactly what we got doing it by hand. And you saw the ways to write that. And so again, we have 99% confidence that the true interval, the true population proportion is somewhere between 2 and 3%. Okay, let's look at another problem. And let's look at number 22. So now, in a survey of 3,005 adults, so this is number 22, N equals 3,005. And they're 57 through 85 years old. It was found that, okay, so the p hat is 81.7%. Used at least one prescription medication, and it tells you where that came from. Okay, so how many, so in other words, they want to know what is our number of successes. Well, here we go. If 81.7% of our sample used it, we're going to take 0.817 times 3,005. And when we do that, we're going to get that there is 2,455 is our X. Now, let me do this on my calculator. Now, on my calculator, I get 24,056.5875, but I want to round this to the, sorry. Okay, so on my calculator I get 2,455 and 0.085, but you round it to the nearest whole number because your successes when you're asking a question like this can only be in whole numbers. So that answers part A. Part B says construct a 90% confidence interval. And we want to estimate the percentage of adults. So we want to have our confidence interval be written as percents rather than decimals, and that's easy to do. No problem. So let's look at this. So the first thing I need to do is I need to find my critical value. And the critical value for a 90% confidence interval is 1.645. So let's do it. We know that it's going to be our p hat plus or minus our critical z times our p hat q hat all over n. So that's going to be, and let's see, I'm going to do it all in decimals and then change it to percents at the end. I'm more comfortable that way. Okay, if p hat is 0.817, we know q hat is going to be 18.3%. So this is going to be 0.817 times sorry, this is 18.3, 0.183, so all over 3005. My margin of error comes out to be 0.0116. There's a 0 behind it, so I'm okay with this. I'm going to add it to 0.8. And on the top end I get 0.8289. On the bottom end I get 0.8054. Change those to percents. It'll be 82.89% on the top end and 80.54% on the bottom end. And they rounded it to one decimal place, the 3 significant digits. Now, what do the results tell us about the proportion of college students who use at least one prescription medication? Well, if we go back, these were 57 through 85-year-olds. So it's only going to tell us, we can only make inferences about the population with the qualities of the sample. So it tells us nothing about college students. Okay, let's go to StatCrunch and let's do it again. And we'll get rid of that. We'll get rid of that. So I'm going to go stat proportions, one sample with summary. My number of successes is, oh, we calculated that, 2455. My number of observations was 3005. We want to do a confidence interval, but we want to do a 90% confidence interval. Now I gotta fix that. And standard wall is what we want, and there we go. And you can see we get 80.5 and 92.9 are my upper and lower limits, so we get the exact same thing. But you can see we can use StatCrunch to do the heavy lifting. If you enjoy doing the calculations, you go for it, but you will be able to use StatCrunch in both your homework and on the exam. And for the last part of this lecture, we're going to look at how big a sample size do we need. So all we did here was we took our formula for our margin of error and we solved it for n, and it comes up with this. Now, if you've printed out those barrel fold tables and you look under Chapter 7, Sample Size Determination, it's right there for you. So those formulas are there. I will put a copy of these equations and tables in with the exam. So you will be able to use those barrel fold tables. There's way more than you need, but I'm okay with that because then you have to figure out what you're going to use and how you're going to use them. So there's our equation. And so when we've done a trial and we have some kind of idea what p hat is, we use p hat q hat in our equation. But when we have no clue what the population proportion is, we actually use p hat as 0.5. And if p hat is 0.5, q hat is 0.5, so 0.5 times 0.5 is 0.25. If you use this equation, you will never underestimate the number in your sample. You're always going to round the value of n up because you need to meet or exceed that e-value that's needed. This is what we call a conservative estimate, meaning that we won't underestimate it. So let's go to page 314 and let's do number 32 and 34. Now you may notice that I'm doing even numbers. That's because you have the answers to the odds in the back, and the more problems you have time to do, the better you're going to be. These formulas are also on page 307, and in your book, if you look on page 309, they talk about better performing confidence intervals. That's all a wonderful thing, but we're not going there. So let's go to page 314, 32 and 34. Okay, so it's chickenpox is number 32. You plan to conduct a survey to estimate the percentage of adults who have had chickenpox. Find the number of people who must be surveyed, so we don't know N. And we want a confidence interval of 90%. And we want our margin of error to be plus or minus 2 percentage points, which is 0.02. Assume nothing is known about the prevalence of chickenpox. So that's A. So remember, our number is our critical Z squared. Now we don't know anything, so we're going to use P hat Q hat. I'm just going to do this so we have that for reference. All over E squared. Well, in A, we don't know. Let's just change colors here. In A, we don't know what that is, so we're just going to use 0.5. A 90% confidence interval, our critical Z is 1.645. If we have no clue, we'll use 0.5 times 0.5, which is 0.25. And we want this to be 0.02. And this shouldn't be down here, but it should be up there. So let's do the math. And I get 1691.26. So what I'm going to do is I'm going to round that to 1692. I'm going to round it up 1. Now we can't do this. StatCrunch doesn't do this, so we're stuck doing this one by hand. Let's look at part B. And part B says we think that P hat is 95%, which is 0.95. That means Q hat is going to be 0.05. So we're going to do it again. It's going to be 1.645 squared times 0.95 times 0.05 all over 0.02 squared. And I get 321.34, which will round to 322. Now, does the added knowledge in part B have much effect on the sample size? Well, gosh sakes, yes it does. If we had no clue, we'd get almost 1,700 people. If we have an idea that 95% have had chickenpox, we only need to collect 322 in our sample. So it's a very substantial decrease. Let's look at number 34. Okay, a sociologist plans to conduct a survey to estimate the percentage of all adults who believe in astrology. How many people must be surveyed if we want a confidence level of 99%? So we know that means our critical Z is going to be pretty big. That's that 2 point something. 2.575. And we want our margin of error to be 4%. So again, let's review our formula. Number equals our critical Z squared times P hat Q hat all over the margin of error squared. Now, assume nothing is known about the percentage to be estimated. So that is A. So in A, we don't know. So we're going to do our critical Z. And we don't know anything, so P hat and Q hat are both going to be 0.5. And our margin of error is 0.04. We're going to slug out that math. And I get, oh man, I got the log in there somewhere. And I get 1036.03, and even though we just have a little bit over, remember we have to go the next number higher. So 1037 are the number of people we need in our sample for A. Let's look at let's look at B, and B says, what if we know that P hat is 26%, which is also 0.26, so Q hat will be 0.74. So again, let's do it. And I get 797.33. It goes on, but I would round that to 798 people. So notice that when we use 0.5 as our best guess for P hat Q hat, we get a bigger sample. And what that means is that's the biggest sample that we're going to need to get a good study. If we have these preliminary results, our sample size can be a little smaller. It never hurts to have a sample that's too big. What will happen if you have a sample that's too small is you won't meet that margin of error that you want. And when professional pollsters do this, this is how they calculate the sample size that they need. One thing I want you to think about as we do these, as our confidence level gets bigger, notice that our critical Z gets bigger. And so what that means is that we have to have more in our sample the higher our confidence interval. And so in other words, what happens is if you want to be 100% sure, you can say, well, it'll be 0 to infinity. And I'm 100% sure that the true population proportion is in there. But that doesn't tell us anything. So if we want to be 99% sure, our confidence interval is pretty wide. If we would only want to be 80% sure, our confidence interval will be much more narrow, but also our chances of capturing the true population proportion get much, much smaller. Now, if we have that, our confidence interval, and we want to find the point estimate, what we're going to do is we're going to add the upper confidence limit and the lower confidence limit, and we're going to divide by 2. That'll give us our p-hat, which is in the middle. If we want to find our margin of error, we'll subtract those and divide by 2. So think of it, our confidence interval is like this. And if we want to know the middle, this is what we'll do. If we want to know the distance from the middle out, we find the difference and divide by 2. So here's an example. And so we looked at people, and we know that our confidence interval is 58 to 81. So let's use that to find our p-hat and our margin of error. So we're going to add the upper limit to the lower limit and divide by 2. So here is our p-hat. So our p-hat is going to be about 69.5 or 0.695. Now our margin of error is going to be about 11.5%. So we could write it as 69.5% plus or minus 11.5%. So here's our p-hat, and remember this is our error. Okay? So what have we done? We've talked about point estimates, we've talked about confidence intervals, we talked about confidence levels, we talked about critical values, we talked about margin of error, and we've talked about sample sizes. So good luck with 7.1.